Picture this, you've built a smart irrigation system with an ESP32, sending soil readings every minute to the cloud. The farmer sees dashboards, sets rules, and everything runs smoothly. Now imagine an attacker intercepts your Wi-Fi traffic, injects fake data, and triggers the water pumps at midnight. Crops are ruined, water is wasted, and your system loses all credibility. That's what insecure IoT looks like in the real world. In this lesson, we'll break down the core of IoT cloud security, authentication, encryption, and platform safeguards. By the end, you'll know how to protect your ESP32 projects from becoming easy prey, and more importantly, how to think like an engineer who designs for both reliability and resilience. IoT systems are different from laptops or phones because they're often small, unattended devices pushing sensitive data non-stop. An ESP32 streaming sensor data over public Wi-Fi is like leaving your house door unlocked while posting your address online. It's an invitation. Attackers know these devices are rarely updated and are easier targets than hardened PCs. Compromised IoT systems can lead to financial loss, safety hazards, and privacy breaches. When you design with ESP32, always think, if this device gets hacked, what damage could it cause? That mindset will guide how seriously you take authentication, encryption, and platform security. Authentication is simply proving your device is who it claims to be. Think of a nightclub bouncer. They check your ID before letting you in. IoT works the same way. API keys are like simple guest passes, easy but dangerous if leaked. Tokens, like JWT, are time-bound, so even if stolen, they expire quickly. Certificates with TLS are the gold standard, where your ESP32 presents a digital ID card signed by a trusted authority. Cloud platforms like AWS IoT Core or HiveMQ require this for serious deployments. The important takeaway: never hardcode plain keys into your codebase. Store them securely and rotate them regularly. Imagine mailing a letter with your bank account details written on a postcard. Anyone handling it can read your secrets. That's what happens if you send IoT data without encryption. TLS solves this by putting your message inside a locked envelope. Even if someone intercepts it, they see only gibberish. With ESP32, enabling TLS in MQTT or HTTPS ensures data confidentiality and integrity. Yes, it costs extra memory and processing, but the trade-off is worth it. A real-world engineer will always prefer a slightly slower device over one that silently leaks customer data to attackers. Even with device authentication and TLS, cloud platforms add their own defenses. Think of them as security guards inside the building. Each ESP32 gets unique credentials, so if one is compromised, others stay safe. Role-based access ensures a sensor can only publish, not subscribe, preventing attackers from hijacking command channels. Platforms can also revoke a compromised key instantly, much like canceling a stolen credit card. When designing IoT systems, you don't just rely on device security. You architect with the assumption that layers of defense will catch what one layer misses. One mistake I see often is students uploading ESP32 code with plain API keys straight to GitHub. That's equivalent to leaving your house keys taped on the front door. Instead, keep credentials in config files ignored by version control. Another bad habit is disabling TLS certificate checks to make it work faster. That leaves you open to fake brokers impersonating your server. Always test with TLS enabled, even if you need to optimize memory. My personal tip: if using AWS IoT Core or similar, automate credential rotation. Assume your keys will expire. Design your system to refresh them gracefully. Here's a quick comparison of authentication methods. API keys are simple but least secure. Tokens are safer since they expire. Certificates with TLS provide the strongest protection, though they need more setup and resources. This table should guide you when choosing security levels for your ESP32 projects. For hobby projects, API keys might be enough. But for deployments that handle sensitive or business-critical data, you should always aim for certificates and TLS. The best way to understand security is to experience both sides, secured and unsecured. Start with a secure weather logger. Connect ESP32 to Adafruit IO or HiveMQ using TLS and dedicated API keys. Then, for contrast, run the same project without TLS and capture traffic in Wireshark. You'll be shocked at how exposed your sensor data is. Finally, try role-based control. Configure one credential to only publish and another to only subscribe. When you swap them, the platform will block unauthorized actions. These exercises will give you a visceral understanding of IoT security far beyond theory. Before wrapping up, I want you to think critically about these questions. If someone stole your ESP32's API key, what's the worst-case outcome? Could they control actuators? Could they exfiltrate sensitive data? Second, how would you design a secure IoT system that runs in the field for years with minimal maintenance? And third, how do you balance resource trade-offs, like TLS memory usage versus leaving your traffic exposed? These aren't abstract questions. They're the exact dilemmas you'll face when deploying real systems. Reflect on them, because your answers will shape your engineering decisions. IoT security is not optional. It's the foundation that keeps your projects trustworthy. In this lesson, you saw why ESP32 devices are attractive targets, how authentication methods protect device identity, why encryption in transit is critical, and how platforms add additional safeguards. You also learned common mistakes to avoid and practical ways to test your systems. Carry this forward, build with the assumption that attackers are always watching, and design your ESP32 projects with resilience, not shortcuts. That's the mark of a professional engineer.